So, welcome back. This is the last segment of the lecture 1. And the lecture 1, let me recall, is devoted to the review of the previously covered material, the material that will be tested on the coming up exam. And therefore, I just wanted to make sure that we are still on the same page and you have very good idea what was done in this class, what are the expectations in this class, and what kind of the problems you can expect on the examination. So after this review, we will return to the regular lectures and we will be covering the remaining part of this course, like it's supposed to be. So let me now begin with this problem, and I believe this is the problem 5. And let's write it down. Evaluate the following complex integral. And the integral is just simply c. And here we put here z, dz, dz divided by z to the 6 minus 1, where the contour c is given by the formula. So this is actually a circle. So that one is equal to z minus a equals to a, where a is a given real number, is larger than 1. And the contour, of course, is positively oriented, and we will be solving this problem now. Solution. So let me first make sure that we understand what is the situation. Here we have the contour, so let me make a small drawing on this contour. So this is my x-axis, this is y-axis. So suppose my number 1 is here, the number a is here. It's larger than 1. So I will be here. Where is I? So here, this is my I. And now we have the contour, and the contour is the circle. Notice that 0 is belonging to this contour, so the circle will look something like this. This is our circle, so this is my contour C. And now you can also notice by inspection that Z6 equals to 1 has 6 solutions. 6 has 6 roots. 6 roots. Let's denote it, all those roots. So let me make sure that we put them correctly. So I know they all have to be located on the unit circle. And these roots, now let me put them down, will be like that. So start with the first one. So 1 is definitely such a root. Then of course there is this place here, this root. So this is my z0 is equal to 1, and this one is z1, and we know even what it is. This is just 60 degrees. Here we have 60 degrees, so this will be equal to 1/2 plus square root of 3 by 2i. And then of course we have on the opposite side, we have here another root. This is my -1, and here we have a conjugate root. Call this one is here, and the opposite side here. So we have here, this will be my z2, this will be my z3, this will be my z4, and this will be my z5, which is exactly similar to the similar to the number 1, except it is minus square root of 3 by 2i. So we have all the roots, sorry, I, okay, plus, sorry, minus square root of 3 by 2i, okay, something is, okay, I, nice, it's kind of making me trouble this time. And of course, if I look at this integral, I understand that the main tool that we'll be using in order to prove, let's say, to compute it, it will be the Cauchy integral formula. So maybe let me make a short margin. I put here like a short margin and put it like this: Cauchy integral formula. Cauchy integral formula. So what is this? That in such a case, if you have an integral, I don't want to use the same contour, so like put it like a c with a tilde, and then we put here f of z standing up, and in the bottom z minus z0 dz. So this integral, as you remember, is 2 pi I, and here we have here f evaluated at z0. So that means this formula gives you the answer to the problem of integration. So here the contour looks something like that. This is my contour c tilde. I have the point z0 inside this contour. The function f of z must be analytic, and in such a case the formula gives you the answer to the integration. But in our case, we have not one, but we have 3 such points, 3 inside the point. And then first notice the following, that actually z6 minus 1 can be written as z minus z1. I will just use the notation like a z1, z2. They are all evaluated, but I will just simply write it down in such a form that you understand that in our computations, yeah, we have more, let's say, like a 6 roots 5, and the last one is z minus z, z5, z0. Sorry. I started wrongly, so. Okay, z0, z minus z1, 6 roots, so z2, then you have here z minus z3, and then we have problem, this is z minus z4 and z minus z5. So it's a kind of a long formula, so it's easier. So for example, here we have a three roots that are essential, and this is number 5, 0 and 1, which are inside this contour. So let me first do the observation that it is possible to take a small contour. So I put here like this little small contour here around the point z5, small contour here about the point z0 equals to 1, and the small contour here about the point z1. So call this contour, this will be like a contour, call it 5, because this is corresponding to the 5th root. This one is c0 because it corresponds to the root 0, and that one will be c1. So we have 3 such contours, and since the expression that we are integrating is analytic on the area between the little contours and the big contour, then we can immediately rewrite our integral and write it down that this integral, this will be z dz, and this will be z6 minus 1, will be equal to the sum of the 3 integrals. So the first one will be the integral of a little contour here, C0, and this will be Z dz, and this is Z6 minus 1, plus contour over contour C1, integral over contour C1, this is Z dz, and then I have here Z6 minus 1, and then I go to the last one, which is C5, and that corresponds to the fifth root, and this is again the same expression minus 1. Interestingly, now we need to represent this particular integral in such a way that Cauchy integral formula can be applied. So let's suppose that we are dealing here with the little contour. So suppose zk denotes the point, the root, let's say, call it like this, the root of this equation surrounded by the contour ck. Okay, this is surrounded by the contour ck. So of course, in such a case, what do I need to do? I need to, in certain way, let's look again, I need to eliminate from that one, from this expression, this root and put it down. So let me write it down. So I need to take this from this product here, this product, I need to make from this product the root zk, means the term, the factor containing z minus zk, and put it in the denominator. So that means let me write it down. I will write simply like this. This is Z6 minus 1. It will be the same, and I put here Z minus ZK in the bottom, and in the top I put here Z, and then this must be the product of all these other factors. But this is kind of a complicated, so I will just simply write it down. I put here Z6 minus 1, and then I put here Z minus ZK, and that simply means I have here a simplification. That means you will need to simplify that factor here from this particular expression, from this particular product. That means it will be eliminated, but it is more convenient to write it down like that. So let me again rewrite it down. So I will write it down using this notation. So this will be like this. This will be Z minus ZK, and here we'll have here Z times Z minus ZK divided by Z6 minus 1, and you immediately realize that is your function f of z that you are computing, that appears in the Cauchy integral formula. This function is actually given by that formula. However, you cannot just simply substitute here the value of z0, because you didn't do this simplification. You just avoid doing this simplification. However, you know very well that since the simplification can be done, so the limit, since, put it like this, since the limit, and this I put here limit, and I put here z to the 6 minus 1, and this will be z minus zk, and this is z goes to zk. This limit reminds you nothing else than the definition of the derivative of the function z to the power 6. That's exactly the derivative at the point z6. So that means I can write it now. This is equal to d dz at the point z6, evaluated at z is equal to zk, and we know how to calculate it. This will be z to the power 5, and that will be zk. So we have the value. We know what will be the value of the function f at zk. So f at zk will be equal, and that's easy now to write. This will be just simply substitution. Here we are getting zk, and then here I have here 5, so that means 6zk5, and that is my, sorry, seems like this is not really put it like this, 6zk5, and then I can multiply it just for the convenience by zk and put here again zk, and since zk to the power 6 is 1, so I'm getting that this one is equal to 16zk squared. Very nice. So we have the value, and now we can return to our integral, and the integral can be now directly computed. So let's write it down. Integral over c, this will be z, and this will be z6 minus 1 dz is equal, and I can consider this as a sum of 3 integrals that were indicated here, and these 3 integrals here, you see this is those 3 integrals, we will compute each of them separately using the formula that was derived above. This formula provides us with the answer. Oh, what's happened? Everything disappeared. Okay, this is 2 pi I, and now we start with the point number zk. So this is z0 is here, so this will be like a 1/6 times 1 squared. Then you have here next one 1/6, and this will be for z1, and this will be z1 squared. And then you go further, and you are getting here, this is equal to 1/6, and this will be z5 squared. Oh, so let me pull out this 2 pi I divided by 6, and here I'm having 1, and this is plus, and where is the z1 squared? Let's go further, let's go back. z1 is here, so z1 squared is z2. This is here, this is z1 squared. So we have here z1 squared, and that means this is going to be z2, and this is going to be z4 similarly. And then we continue, we write it down, this is pi I divided by 3, this is 1, and the first one, z2 is equal minus, so maybe I remove me this plus, minus 1/2, and this is plus I square root of root by 2, and that one, the second one, is conjugate of that one. This is still equal, minus 1/2, and this will be minus I square root of 3 by 2, and then we do the simplification. You see these two cancel, and then it's 1 minus 1, so this is also equal to pi I over 3, 1 minus 1, and we got result 0. So the problem is finished. The problem is finished. I hope you enjoy it, and then since we like this material so much, we go and do another problem, similar one. So let me fix the image first. So properly spread it and move it to the beginning. Okay, so let's go to the next problem. Start with the problem 6. So again, evaluate the following complex integral. And the integral is like this. This is c, and this one is dz divided, and here we have here z squared plus 1 squared, where c is equal to the set of all z such that z minus I is equal to 1/2. So let me write solution. And let me illustrate first. So let me illustrate the contour. And then, of course, I would like also to show where are the roots of the denominator. So here, let me start with the coordinate system. This is my coordinate system, and then it's crooked. Better. So I have here, put it like this. This is my 1. This is my I. And then I have here the contour C is something that goes here around the point R. Radius 1/2. This is my contour C. And then where are the roots of the equation? So let me write it down. The equation. So here we have here z squared plus 1 squared can be written as z plus I square times z minus I square. Z minus I square. Okay, perfect. So now what we do, we will transform my integral, the initial integral. So this is integral C, and this is transformed to a new form. So call it like this. This is dz, and then I put here z squared plus 1 squared. This is going to be equal, and I write it down in the form that this is equal to 1 divided by z plus I square divided by z minus I square. I put the z here, and we can see that we can use the generalized Cauchy integral Cauchy formula. Generalized Cauchy formula. Cauchy formula, and that provides you with the following. So if you have here function f of z, and this is z minus z0 with the same picture as before, except now you put here n plus 1. This is going to be again 2 pi I divided by n factorial, and this will be n derivative of f at the point z0. So here we have the power, which is 2. This is equal to 2. So we need to understand that in our case, the answer here will be 2 pi I divided by 1 factorial, and this will be f prime of I. That's the point z0, where f of z is exactly the expression standing here. That means this is our f of z. That one. So that means, let me compute it. This is equal to 1 divided by z plus I squared. So we compute easily the derivative. The derivative is equal minus 2 divided by z plus I to the power 3. Then that implies that f prime of I is equal minus 2 divided by 2 to the power 3 I to the power 3, which provides me with the 1/4 I. This is 1/4 I. And now we can write the answer. Therefore, this integral of c dz z squared plus 1 squared is equal, and we are getting here that exactly 2 pi I times the first derivative at I, so this will be times f prime of I, which gives me 2 pi I times 1/4 I, and we are getting this is pi over 2. This is equal pi over 2. And that's the answer. So just to complete the... So let us modify the last problem and make it kind of a little different. So this kind of the problem could be given, let's say, to you on the exam, coming up exam. So the problem, let's start it. Problem. What's happening? Let me check. Okay, problem works now. And I believe it's number 7. So underline, it's evaluate the integral and the integral is just simply this. The contour will be the same as in the last problem, except I add at the numerator, I add the function sine z. So this is again z squared plus 1 dz, where c is exactly the same contour. So this is z minus I, absolute value, is equal to 1/2. So we can just go directly to solution and write the answer, solution. So before we do the answer, we just simply write it down. This will be c, and write it down, sine of z dz divided by z squared plus 1 square. I rewrite it in the form that will allow me to apply the generalized Cauchy formula. So this is z plus I square, and as we did it before, I don't need to repeat it, and put here like dz. So now, of course, we understand our new function f of z is this one. So we just simply can write the answer and then evaluate it correctly, 2 pi I, and 1 factorial is 1, so this means this is f prime of I. So I need to compute this. So let me do it. So my f of z is equal to sine of z divided by z squared plus 1 square. Very good. So f prime of z is equal, so first one is a cosine z divided by z squared plus 1 square, and then I have minus 2, and this will be sine of z divided by z squared plus 1. That's not correct. That's not correct. So no, that's not a big problem. Let's remove all these mistakes. So that was not correct. So we have to be careful. Plus I square. So f prime of z is equal cosine. Now it's going to be correct. This is z plus I square, and this is minus 2 sine of z, and that one is divided by z plus I cube, and that's correct. So we can just simply evaluate this f prime of I, and of course we can use it to write the answer. So what do I get? I'm getting this is cosine of I divided by 2 square I squared. Then you have minus 2, and this will be sine of I divided by 2 to the power 3 I to the power 3. And then, what do I get? I'm getting here that this one is 1/4. My I to the power minus 2 is minus 1, so let me write it down. This is equal minus cosine of I. Here I have 1/4 already taken, so this means simply I have here in the bottom I. So I put here like this. This is minus, and this is sine I. Oh, and that one is I to the power 3, so it will give me plus. And I have another I, and this will be closed. So let me finalize it. So what I'm getting is 1/4, and then cosine I is nothing else than minus cosine hyperbolic of 1. And here sine I, so this will be plus, and this will be I sine hyperbolic of 1 divided by I. And then of course we can simplify it. So this is nothing else than sine minus cosine, and this gives me e to the minus 1. E to the minus 1. Yeah. So let me write the answer. So our answer is that we have here the integral over c sine of z dz z squared plus 1 squared is equal to 2 pi I times 1/4 e to the minus 1. Simplified, you are getting here this is pi I divided by 2 e to the minus 1. Finished.